Howdy iOS programmers. In this Oracle Mobile Cloud Service episode, we're going to show you with the iOS SDK what you need to do to get your iOS app working with the Mobile Cloud Service Data Offline and Synchronization API. Thanks for joining me. I'm Chris Murrett from the Oracle Mobile Platform team. Now, in a previous episode, we gave you a good overview of the different components that are needed to make use of the data offline and sync capabilities on a mobile client. And in those episodes, we describe what and where those components exist, namely on the mobile client and the server side of Oracle Mobile Cloud Service. In considering the mobile client itself, you might remember we also discussed what the broad steps are to configuring your mobile app for data offline and sync. You need to include and configure the MCS iOS SDK, which we covered in an early episode already too. From there, if you're working with a custom API on MCS, you need to define the sync policies on the mobile client to use. Or conversely, for a storage API, the policies are hard-coded for you. Finally, and the focus of this episode on the mobile client, you need to call the iOS SDK data offline and sync libraries to consume the remote MCS custom APIs you want to sync with. So for teaching purposes, it makes sense to start with the sync policies. For the remote MCS custom APIs, we want our mobile app to sync with. So let's consider those sync policies now. Also for teaching purposes, let's say we're building, an app for couriers that lists the deliveries they need to make to customers. Now, as couriers are constantly on the go, their mobile devices often lose connectivity, so their data offline and sync API in this case is an ideal use case. In order to support this scenario, on the MCS server side, we have a custom API that at the top level has a collection endpoint that returns delivery dockets for the courier, and then individual endpoints to get, post, put, and delete the individual delivery dockets. With this custom API in mind for sync, we then need to go in and define our sync policies in the iOS application. So let's first look at how you specify these specifically in iOS. So within our mobile application, we locate the MCS omc.plist file we configured when we loaded the MCS iOS SDK earlier. Within the mobile backend block to set the sync policies for custom APIs exposed to this MBE, we include a synchronization block like the following. Overall, the sync options are split into three sections: global policy settings, one or more individual policy sets for specific APIs you list, and an optional default policy block. So for the path mobile custom courier, which relates to our MCS server-side custom API for our application, we can see that we define sync policies: fetch from service on cache, miss or expiry, expire after 180 seconds, and queue if offline. When listing policies for individual APIs, note the path string used here, mobile custom courier, then $*. The path parameter takes static paths or wildcarded paths indicated by the stars as you can see in this example. If, for example, we set the path to mobile custom courier without any stars as wildcards, this means the relating policy will apply to a custom API that starts with mobile custom courier, but nothing else such as mobile custom deliveries or even a sub-resource such as mobile custom courier deliveries. Alternatively, if we use the same path but append 1 star as a wildcard, this will match any resource at the same level and +1, such that mobile custom courier and mobile custom courier deliveries is accepted. Finally, if we use a double star for the path, this will match any resource at the same level and any nested resource too. You are free to define other sync policies for other custom APIs. Or, as we can see here, I've included an optional default policy block, and that will apply to any other APIs you attempt to access via the data offline and capabilities but haven't defined a policy set for. Having set up the sync policies in your iOS application in the omc.plist file, now let's look at the code to exercise those policies and access the remote MCS APIs. So to work with the sync classes, the first thing you need to do is to get a handle on the mobile backend objects and synchronization objects provided by the MCS iOS SDK. Now, as you're typically going to use these across your application, you can define these in the application delegate and make them available to the rest of the application. So in the app delegate header file, we add the following two imports: OMC mobile backend and OMC synchronization. And then we add the following properties for the mobile backend and synchronizations objects. I'm going to call them MCS MBE and MCS sync. Next, in the app delegate.m or implementation file, we then first import the following classes: And once done, within the application did finish launching with options function, we can initialize the properties you just created in the app delegate header file by calling the mobile backend manager, shared manager, default mobile backend method, then using the mobile backend to access the OMC synchronization object. From here, you build out your app, maybe including a login screen, or maybe the app doesn't require authentication. We've covered how to authenticate your mobile users in earlier videos in iOS, and we won't cover that again. So for this video, we'll cheat. We'll quickly import OMC authorization, then make a call to authenticate the user anonymously against MCS. Now, it is worth noting, however, that the device's local cache is per user, anonymous or not. In this way, two different users logging in, or a user and an anonymous user, won't see each other's data. Now, at some point in your logic, you need to start the sync engine provided by the SDK. So you call the sync object's initialize method. This method is important as not only does it prime the sync engine, it also kicks off the periodic refresh policy and the background thread we discussed in the earlier episodes around sync policies. And it is important that you call this initialize method before you start fetching data from the various APIs provided by the synchronization classes. At this point, before we continue, it is worth running the app through the debugger as is and see what effect this code has. All of the MCS SDK methods include logs and instrumentation, and via the Xcode console, we can actually see what happens under the covers. Remember, the data offline and sync API is nearly an automagical API that does things for you under the covers. So looking at those logs will tell us what's actually going on. In accessing the mobile backend, we can see the mobile backend manager initializing with the OMC plist entries you created earlier. On stepping over the authenticate anonymous method, we can see the logs are checked to see if the device is connected, then a remote anonymous authentication check against our MCS server. Now, the important output for us in this video on data offline and sync is the output via the initialize call. Here we can see the result of some of the things you've defined in the OMC plist file, such as the initialization of the periodic refresh thread to refresh expired data from your MCS APIs. Now, that last message is an interesting one because it tells us when the periodic refresh mechanism is next going to fire. If you remember, we configured that in the OMC plist file. We set it to 60 seconds. And if we literally sit for 60 seconds, we will see that periodic refresh fire again and the following log. Now, that will continue to fire until the app is suspended or stopped. From here, let's say our goal is to show the courier delivery data in, well, maybe a simple view controller and containing a table view. Now, I know you're an expert iOS developer and you're going to build a better application than just showing data in a table view, but for teaching purposes, this will do. As set up for this, in the view controller header, we've added the UI table view delegate and the UI table view data source protocols. And in the view controller implementation file, you can see the UI table view added as a bound property. And a little bit further down, as required by the table view, you can see the number of rows in section method and the cell for row at index path method. Now, as you agree, very simple table view implementation, displaying nothing more than dummy text at the moment. Let's now add the code to work with the SDK's data offline and sync API. First, let's add the required headers for the code we're about to add and explain. Next, when the view controller is first initialized in the viewDidLoad method, we want to fetch the data from the remote API using the data offline and sync SDK. So I'll add a function call to a new function, sync delivery API. And we'll code our logic into this function just to keep its logic separate from the viewDidLoad. With a quick insert of the code, you can see that we first grab the app delegate handler to access the OMC synchronization object called MCS sync here that we created earlier. From the sync object, we call the open endpoint method to map to our remote MCS custom API, courier API, which we also defined in our sync policy files, and the specific endpoint resource deliveries we want to access. The first parameter, OMC mobile object.class, defines the object types we will receive back from the remote call in a moment. To be clear, the open endpoint method is not yet making the call to MCS. Rather, the OMC mobile endpoint object is the handle to that remote API, which we will now call more code to act upon. To act upon the remote endpoint, we use one of a set of builder classes provided by the SDK. Which builder class you choose depends on what the remote endpoint exposes. You might remember we said in the previous episode, server-side custom APIs can as example return objects or collections. So for an object, you would use from the SDK the OMC fetch object builder class. But in this case, for the courier deliveries API, as is returning a collection of delivery dockets, we instead work with the OMC fetch object collection builder class. With a handle on the builder collection class from the endpoint, you can do things like set the URI parameters for the remote call via the withParam_name method. Though in this case, our remote API doesn't have any URI parameters, so I'll leave this commented out, though you can see the example. Finally, we call the builder execute fetch on success method. This method is what actually initializes the call to remote service and fetches the data. And you will give it a success callback, which will be passed to return collection as an instance of OMC mobile object collection for you to use. Or you also can provide a failure callback where you can handle any issues or errors. In the success callback, as we want to use the return collection within the view controller, we write it to a local collection object delivery collection. Finally, in the success block, we also log the success to the console. So, we can see something and use Grand Central Dispatch to refresh the table view by calling its reload data method. So we then modify our table view number of rows in section method, such that if the delivery collection object is null, the table view won't print any objects. Otherwise, it will list as many objects that were returned in the delivery collection instance. And finally, in our table view cell for row at index path method, rather than writing dummy text to each cell label, we instead retrieve the array objects from the collection using the getMobile_objects method. We then access the specific array element that maps to the current row in the table view being displayed. And as the remote object is a JSON object, we use the JSON object method to convert the OMC mobile object to a JSON NS dictionary and extract the title of the delivery item to show in our table view's current cell being displayed. Now, this is again a great point in our application to run it and watch the logs to see what happens under the covers. Like previously, we can see the code executed in the app delegate, an anonymous login against MCS, and the sync engine being initialized. But now, on accessing our view controller, our sync delivery API function is called by the viewDidLoad method. Only once we execute our fetch object collection builder execute fetch on success method do we see our first set of log entries. You'll remember our fetch policy for the courier API is fetch from service on cache miss or expiry. This implies the SDK will attempt to access data from the device's local cache first, but if it finds the data missing in the cache or the data has expired in the cache, it will go to our remote custom API in MCS. Now, in the logs, we can see a cache miss for the data identified by our API endpoint courier. And we can literally see the API preparing itself to make a network call as it can't find the data locally. Then, when eventually the success callback is called, we can see at this stage the actual HTTP GET. Okay, so that just occurred before the success callback, then the callback was called to call to our remote URL and the HTTP headers that were used in that call. And after that, we can see the responses listed, along with its HTTP headers and our collection payload coming back from MCS. Finally, you can see the data written to the local cache for reuse next time. So, all's good so far. Now, if we continue to sit here with the app running, we'll see that periodic refresh being called approximately every 60 seconds. If we wait long enough, thanks to the fact that we set the expiry period for the data returned from this API in the OMC plist file to 180 seconds, after 180 seconds since the fetch and during the next periodic refresh, we will see in the logs that the periodic refresh flushes the expired records and goes back to MCS and our remote custom API to get an update of the data from the server. Now, it uses an internal optimized method to do that called batch sync that pulls down the refresh data from the server. So from here, our last task is we've potentially downloaded this updated data from the server and it's sitting in our cache, but we've not updated the data in the table view on the screen. Now, there are different ways to achieve this, possibly with a refresh button, or we can add a timer to the view controller. And then in the viewDidLoad method, initialize the timer to fire every 30 seconds, calling a selector function update delivery. In that selected timer method, if fired and the delivery collection is initialized, on the delivery collection OMC mobile object collection method, we call its reload resource method, which refreshes the instance from the underlying local cache data, which was just recently updated. And then like previous, we ask GCD to reload the table view to show the latest values in the collection. So, beyond setting up the sync policies file and doing some initial fetch of the data in a couple of lines of code, adding some code to retrieve the actual value we want to show in the cell, and some code to remind the table to occasionally periodically update itself, think about all the code here that you didn't write. No code to set up and manage core data or the SQLite database on the device. No raw HTTP calls and dealing with stale data and flushing data and reloading it. No threading code to fire periodic refreshes. There's literally hundreds, if not thousands of lines taking care of you here. So you, the mobile developer, can focus on building a compelling app over worrying about what is essentially a plumbing task, and a very complex plumbing task at that. Thanks for joining me in this video. Hope you're starting to see the power of the Data Offline Sync API. Catch you in that next video very soon.